That's the radius of the Earth. Okay? And instead of thinking of the Earth coming in like this, let me consider as if the energy is going like that. I don't know, maybe this will make it easier. Right, so that's J here, and that's J over there. In other words, instead of thinking of the energy coming in like this, I'm just going to think of it as going like that. It's just a minus sign thing that I don't want to deal with. Okay? So over here at the top, right, that radiation is perpendicular to that 1 meter square. So it's J times the area of that. But over here, right, if you consider like an area like this, right, this J is at an angle. It should be, when you write the intensity is energy per unit time per unit cross-sectional area. That cross-sectional area is perpendicular to the radiation. So we have to deal with the fact that, there's a curvature to the Earth, right? So I'll just consider, instead of thinking of, I'll just consider, instead of the energy coming in like this, I'll just consider it going that way. In the end, it's the same, right? And then what I'll do is I'll say, okay, so this is the radius of the Earth over here, right? That's the Earth, we know that. And I'm going to go from here to there. And I'm going to call this angle theta. Right? And I will consider, a chunk of the surface of the Earth like that, right? And then I'm going to go like this. Maybe I'll use the same color. And then I'm going to call this angle here d theta. But really, can I erase all of this? Because this is not, I won't need this anymore. Now I guess you understand the picture, right? Now, this is like a sphere, right? So for this angle theta, what I really have is I have something like this. Right? And then this one goes like that. I really have like a ribbon, like a strip. Like that. Can you picture that? Imagine like a ribbon or strip on the surface of the sphere of the Earth. Okay? So what is this? This radius over here, right? Is the radius of the Earth, right? And so is this over here, right? What is this distance over here? What is this distance? It's an arc length. Slice of pizza geometry, for those of you who have taken physics from me before. I tend to call it the slice of pizza geometry. I mean, right, what is this arc length? If this is R, and this is, I'm calling it d theta, so I guess I'm going to call this ds. But, forget about the d, if that confuses you. If this is theta, what is this length? R theta. So therefore, what is this length over here? I'm going to call it ds. Look at the angle subtended. R d theta, right? It's the radius of the Earth. I guess I can drop the R, right? And the E, right? It's just too many E's. I'll just call it R. You know that means the radius of the Earth, right? Well, I'll just put someone over here. So that's the surface of the Earth, right? Obviously not to scale. That would be a very tall person. Now, what is the area of that strip? Let me call it dA. If I'm going to call this length ds, I'm going to call that dA. So what is the area of that strip all the way around? Imagine you have like something like this all the way around. What is the area of all of that? What's the radius of this thing? What's the radius of this? I can think of this as a circle, so what is this radius here? Think of this triangle. This is R, right? That's 90 degrees. So what is this? And that's theta. I'm drawing this. What's that? R sine theta. It's opposite the angle given. So it's R sine theta, right? So that radius over here is R sine theta. So if I take that strip in blue, suppose I take that strip and I cut it and I stretch it out. It will look like this. And this length over here, this length over here, I would use red for that. This length here is this, which is and what is this? What is this distance all the way around that ring? What's the distance around a ring or radius where this is the radius?
2 pi r sine theta?
Yeah. 2 pi times a little r, which is the radius of that strip, but little r is related to this, right? So therefore, what is the area of the strip? Let me ask you the question again. Maybe by doing this, it's easier for you to see. Now, what is this area? It's just a rectangle, right? Length times width. So it's 2 pi r sine theta. That's this length, and then the thickness over there is r d theta. Are we good so far?
Yes.
Yeah. I'm using what are called polar coordinates. I'm sorry, spherical coordinates. Except that I think in calculus, you call that angle phi as opposed to theta.
Yeah.
You call it theta, but it's the same thing, right? Now, the energy that would be coming into this or going out of this is straight up, right? That's J. Right? This is energy per unit time per unit area. Right? But what we need, right, to consider the energy that actually hits the Earth, we need this one over here, perpendicular to that surface. So actually, I'm drawing it like this now, but if the energy is going out, then it should be going out this way. But this is the vertical, right? Going this way, right? So this is theta. So what I want is the component of this J onto this axis, right? So that it's perpendicular to it, sort of like this. So it should be J, it's adjacent to this angle theta, cosine of theta. So the total flux or the intensity, so if I could call it, let's call phi, I'll just call it flux. Let's say this is the energy per unit time through all of that area. This is really power, right? You can call it dP if you like for power, but I'll just call it that. So the flux through that, only this strip of area, I'll just call it, that would be J. It's really J times the cosine of theta. Actually, if you want the more general definition, I'm not done on it, it's J dotted with that area. So it would be J cosine of theta times the area, dA. But that's just because of the dot product. So that's the flux that's gonna, of radiant energy through this strip in blue. What I want is the total energy per unit time over all of this top hemisphere. Right? Over here is coming in straight, but over here is coming at an angle. Over here is actually missing, like tangent over there. It doesn't even hit. Right? So you get zero contribution over here, maximum contribution at the pole, right? And then less, zero. So what I need to do to figure out the entire, so let me write this again like this. So J is J, right? And then I have the cosine of theta. And then dA is this, 2 pi r sine, actually r squared, right? Sine theta d theta, right? Because I can combine this with this, right? So that gives me an r squared. So this is J times 2 pi r squared sine theta cosine of theta d theta, right? That's, let's say, the flux through that strip of area dA in blue. And what I want is the total flux over the whole hemisphere, top hemisphere. So then I integrate this. So 2 pi r squared, those are constants, J is a constant, and then I have the integral of sine theta, cosine theta, d theta, and now I put in limits of integrations, right? If I consider the very first strip at the top, what's the angle theta for that one? 0. And then I consider that strip, this one, and then the next strip. And what happens when I consider the last strip over here? 90. What's the value of theta?
90.
90 degrees, right? Or pi over 2 radians. So I integrate. Obviously, the energy is not going to hit the bottom surface, right? Coming in from the sun. So this is going to be from 0 to 90 degrees. So this is equals. What is the integral of sine theta, cosine theta, d theta? What is that integral? That's supposed to be simple. Sine square over 2. Sine square theta over 2. You know, if you like, make a substitution, let u be sine theta. So du d theta is cosine of theta, so du equals cosine of theta d theta. So I can take this, right, and I can plug it for this, and I can take this, and I can plug it for that. So this becomes 2 pi r squared j times sine of theta, which is u, times the cosine of theta d theta, which is du. So this is 2 pi r squared j. And what is the integral of u du? U squared over 2, right? And before I plug in the limits, notice this 2 cancels that 2. I get pi r squared times j times u squared, but u is the sine of theta, squared from 0 to pi over 2. And what is this? What's the sine of pi over 2? And 1 square is? 1. And what is the sine of 0?
0.
So therefore all of this is just 1, right? So you get pi r squared j. Which is what we had claimed. You know, this sort of calculation like this, it shows up quite a bit. So I'm doing it so that you make connections with calculus, right? With what you learned in some of your calculus classes, you know, you have, that would be like an area element. You know, you can use spherical coordinates. You can write that as a little patch and then integrate over this angle also. But that's just like this ring. So you're just gonna get a factor of 2 pi when you integrate over that azimuthal angle, but anyway. So next time, I think, I don't wanna say more about that chapter. I'm gonna move on to chapter 18. And we're gonna talk about
Wait, 18 or 19?
19, sorry. No, wait. Yes, 19, sorry. Good. 19, remember how I said we wrote Q equals MC delta T for solids and liquids? But I didn't say anything about the gases, right? We said we gotta be careful about the gases, we have to treat that separately. And we wrote Q equals ML for the phase changes. But what happens if you have a gas and you add thermal energy to it? So because the gas is compressible, the gas can, expand, it can shrink, and as it does that, it can do work. So we have to write down, when you add energy to the gas, we have to take into account the fact that it's possible that it'll do work. Because something very interesting is going to come up. For example, suppose I give you 20 bucks. I'll give you 20 bucks. And you spend 20 bucks. Overall, you're not making any money because you're spending as much as I'm giving you. So what happens if you add, let's say, 100 joules of heat energy into a gas? But the gas, as it receives that energy, it expands, pushing out, and therefore doing positive work. And what if it does exactly 100 joules of work when you gave it 100 joules of heat energy? You expect, right? From intuition, I poured in their heat energy, the temperature has to go up. That's what you would expect. And that's what happens with liquids and solids. But with a gas, because of the possibility that it can expand and do work, considerable amounts of work as it expands, then it is possible that you add to this gas heat energy Q and the temperature stays constant. Because what happens if you give it 100 joules and it does 100 joules of work?
Then there's no
Then
energy.
the energy that you gave it is not going to raise its temperature at all. If it spends as much as it receives, its temperature is going to stay the same. And that's contrary to what we think from intuition. You think, what? You're heating it up, but the thing is not going up in temperature? Right? So, but what happens if, for example, you give it 100 joules of energy and the gas only does 50 joules of work? Then it's like effectively you only gave it 50 joules. And that's what's going to cause it to raise the temperature. So there are various processes that the gas may be taken through where how much is going to go up in temperature when you give it heat energy Q will depend on the process that the gas is taken through. How much work does it do? Right? Does it do any work? Maybe it's not allowed to do any work, and then all of the energy to give it is just going to go up to raise its temperature. So we have to consider those issues, and so we'll talk about that on what is it? Thursday, right? Okay, I'll see you then. You have a great day.